measure for doing quantitative analysis, because then I will now account for where I am and I will somehow scale that. It's quite painful. So from there we sort of said, well, let's create this transform space where I try to normalize this distance metric. So I want to create a transformation from my xy space to go into a new space where it doesn't matter where I am, the same distance would imply the same separation between colors. So that's how the UV space came about. Okay? And in the UV space, you find that, well, these are what the separations of colors look like. Not perfect, but it's a little better than what we have in the XY. And we kind of use this a lot as approximations and say, well, this will just measure some nice, L2 distances and we are happy. It's an approximation and it's good enough. Now, in general, if you want to use these, and typically as you start in the field, color models are typically used initially for coding purposes, right? For coding purposes, if I want to use things, then what is the fundamental notion of video coding or image coding? How do we achieve coding or compression? Most compression models are predictive models. Furthermore, most compression models are linear predictive models, which basically say that I have a model that says that the previous plus some value gives me the next. So rather than sending the previous value, I will simply send you the error value or the difference value. And you take what you have decoded from the previous step, add the new value, and I get a new prediction. That's my recovered image. So if you want to do that, and say, obviously for that you would prefer that these distances are the same everywhere. But you don't want to say that, well, because of this color, I have a completely different energy value for green versus red versus blue. Addition is addition. I simply want to add everything to it. So for video coding, again, this would be useful to equalize things, normalize things. Now, in general, color appearance itself is going to be affected by multiple factors, right? We actually get affected by nearby color. Adaptation is a process that we get affected by, and of course the state of mind, right? Where we are and what we are thinking at that any given time. So here's a great example, right? If you look at an image like this, right? I don't know if you can perceive that, but for me, the yellow in the red region is much brighter than the yellow in the green. So our ability to sense this is based on surrounding colors. Right? So surrounding colors affect our ability to perceive what true color is. Of course, in reality, right, it's the same. There's no difference. But the perception doesn't agree there. Now, even for adaptation purposes, right, keep in mind our ability to perceive color is an integral measure of some unit time. But, keep in mind we integrate only at certain time intervals. It's not something that we continuously do. So if you actually look at this for a long time, right, you have now a stable firing sequence that says, this is the amount of energy that I'm integrating for my spectral response. And that's what we are seeing. And then all of a sudden you switch, right? You see that the original intensity doesn't die out immediately. So look at the red, for example. Okay, when I'm switching, of course, I'm not changing the amount of energy for red. But what you should be seeing is that all of a sudden, there should be decreasing intensity, right? So think of it as a residual carryover. Before you adapt to this, you are now saying that I'm integrating something which is all red. I'm fixated on that. And then all of a sudden you're changing, but now you have to integrate multiple things. So all of a sudden this value is going to drop for a while before it comes back up. So again, this is a problem, right? Our perception is restricted to these time windows, and that's not natural for us. I mean, in terms of color constancy, that's not how color changes. So color constancy is an interesting thing to address in terms of computational problems, right? So coming back to what we did in terms of radiosity calculations, right? We assumed a lot of constancies over there, specular constancies and Lagrangian surfaces, albedo constancies and whatnot. But when things change, what we acquire as an image may not necessarily translate to that. Because all of these are integral measures, and so as a result, we have now say, well, how do I deal with color constancy in my perception or computational scenarios? All right. So obviously, anything that we realize in terms of surface reconstruction and so on and so forth, we want to understand my illuminant description, right? My profile for the illuminant. I need to understand my spectral profile for the object itself in terms of its spectral albedo, maybe, or it may be the spectral radiosity. Okay? And then, of course, in general, I want to perceive multiple kinds of things. What color is the object? What is the color of light? So I want to be able to decompose the scene to actually get these measures back. So color constancy is something that we can actually study, right? So let's say that you have the same scene illuminated by two different lights. Let's say this is white light, maybe this is green. So of course you have something that you're sensing, right? And I can look at sort of regions on this image and different regions on the image and say what are the underlying colors. Right? So we can perceive some colors, and of course the idea is that objects that have some underlying color should maintain a constancy of that color independent of the illuminant. So how do we actually account for that? Now, if I were to look at the actual sensed color in my so-called some normalized color space, right? In this case, my CIE XYZ space or XY space, I would find that if I have uniform reflectance coming off of some object, but my light source is changing, the color that I perceive under different light sources will actually vary, will move around in that space. Okay? Now, if I actually look at a different object under the same light sources, then I would find, of course, the perceived color is different because I'm looking at a different native color of the object, but the way the different lights actually get perceived, the variance of that is not that different, right? So each light source, a common light source, will shift the color in a consistent manner. So if I look at an object under green light, or if I look at the same object under white light, yes, my perceived color is different, but there is a proportional shift in my perception because the underlying object color is the same. And we can actually see this, and people have done this for multiple kinds of objects, right? So things that are natural, they have an underlying natural color, will remain the same, right? So as long as I can somehow remove the effects of my illuminant color, the underlying color of the object will persist. Make sense? Okay. Now, in perception, of course, we also sense things based on neighboring colors. Right? Adjacent colors play a very important role in what we perceive. So what do you perceive here, for example?